Students, welcome to SmartKidz tutorials. In this video, we'll be learning about magnetic effects of electric current. Magnets, as we know, exert a particular force on the objects they attract, and this magnets they have uh, an effect on or relationship with the current. We studied about electricity in the previous chapter of electricity. And now what we do is we see how magnets play an important role in electric current. Okay, so magnetic field around a bar magnet. So we'll look at few examples to show or to illustrate how magnets have a bearing on the current that passes through an object. Okay, so we first come to the magnetic field around a bar magnet. Have a look. There is a bar magnet. A bar magnet will always have a north end and a south end. So we call as a north pole and the south pole of the magnet. So a magnet always exerts an influence around the region surrounding it. We know when we place a magnet, this is a bar magnet, but usually we come across magnets of various sizes and shapes. Usually we get small magnets, okay, like the magnets that we stick onto our fridge, onto our cupboards, okay. Now these the magnets which are there. If you notice, if you take any object that can be attracted towards a magnet, like a needle, you notice that as you bring the needle closer and closer, the force, the attractive force, or the force that pulls it closer to the magnet gets stronger and stronger. How strong it gets from a particular distance from the magnet depends on the strength of the magnet. If it is a very powerful magnet, then from a very far, from a big distance, the object, like let's say in this case, we make use of a pin. The pin will get attracted. Okay, and the closer you bring the pin towards the magnet, you will notice that the force that is attracting it towards the magnet is getting stronger because you feel a pull. Okay, you feel a pull as you bring the magnet closer and closer. Now that shows you that there is a field around the magnet because it's not just from one side you can that gets exhibited, as in the pull, the attractive force. If you move the pin around the magnet in a particular radius, let's say we take a radius of 2 centimeters, and at that 2 centimeters, the strength of the magnet is strong. That means the attractive force is strong. If you move it along that radius of 2 centimeters around the magnet, you will feel the force of the magnet equally. As you move it away from it, it will reduce all around the magnet at that particular radius. Let's say you move it from 2 to 3 centimeters, the attractive force will weaken. From 2 to 1 centimeters, if you bring, it will be the strongest all around the magnet, not just at one end of the magnet. So this shows you that there is a circular field which we call as the magnetic field around the magnet. And that is like an area where the strength of the or the power of that magnet is exerted. That reduces as the radius from the center of the magnet, increases. It means the field gets wider and wider. If you have a look at this, what I'm trying to say over here, this is sorry, this is a bar magnet. Okay, and you see how the movement is taking place. Here you have these are the fields, these are the magnetic lines that we can see this, and we see that it with each circle, the radius or the distance from the center, the circumference of that circle increases. And as it increases, the strength of the magnet, that means the attractive force of the magnet, also decreases. Anyways, so this is the known as the magnetic field, these lines over here. An area where the influence of the magnet is supposed to be exerted. We can't see them, they're invisible, but we can definitely feel them. So magnetic fields have both direction and quantity. If you notice over here, see, it shows you it's moving from N to S. N stands for North Pole, S for South Pole. So that means the magnetic field lines are from North Pole to South Pole always. Okay, North Pole. You see, actually, you see these big ones that shows you that this magnetic field is moving out of the North Pole and is coming or converging at the South Pole. Have a look. Okay, so that is why it is said it has got direction and it has also got quantity, because the strength of the magnet will decide how great is the magnetic field, how many magnetic lines are there. Okay, and as I mentioned to you, the field always emerge out of the North Pole and always merge into the South Pole. Now inside the magnet, the field is from South Pole to North Pole. See, why it is from South Pole to North Pole? See, where does it emerge from? It emerges from North to South. So it moves out from the magnet North Pole and then moves into the magnet South Pole. Now inside the magnet, how it will move? South to north. That is why it is said that inside the magnet the field is from south to north. Outside the magnet it is from north to south. Okay, understand? From north it moves towards south and then it has to complete its circle. So it moves inside the, I mean, when you refer to inside the magnet, from south to north. Okay, there is a difference over here. Moving further, so this is the from what we saw last time, the previous slide. This is North Pole, South Pole. This is an entire bar magnet, and from the North Pole you emerge this imaginary lines or this invisible lines, which we refer to as magnetic fields. And notice with each one it expands. The magnetic field expands. Okay, so strength of the magnetic field is determined by the closeness of the field lines, how close they are to each other. If they are very close to each other, it's a strong magnet. If the distance is great, then the magnetic field will be weaker. As a consequence of that, the magnet is considered to be a weak magnet. Okay, so always you can try this at home, even if you will, irrespective of whether you have a bar magnet or not. You can take a magnet and you can try checking out on a piece of paper as to the different lengths or the different distances from the magnet, how the magnetic field changes, as in the change in the attractive force of the magnet. Here, now this is an experiment to show how the magnetic field lines which we are talking about, which we say invisible, using iron filings, we can actually see. You have a look over here. These are the iron filings which are being put all around the bar magnet, which is marked north, south pole. And you see these lines, there were these fine lines. Okay, they don't really complete. They're not seen over here, but yeah. So you see these iron filings actually arrange themselves in that magnetic field. So they actually show us that there is a magnetic field. Similarly, when in this case there's a compass with the needle pointing north-south, and when we bring a bar magnet close to it, the needle gets deflected. Now, if we bring the north pole of the bar magnet closer to the compass, the needle will get deflected in such a way that the south pole will point towards the north pole of the magnet, because opposite forces they attract each other. Now, magnetic field is a straight current carrying conductor. So coming now, we've understood about magnets, how they have a magnetic field, how uh, various elements or various substances can get attracted towards magnet depending on the strength of the magnet, which depends on the magnetic field. Okay. Here we look at how a magnetic field is generated in a conductor which is carrying current, and this is a straight current carrying conductor. Okay, because we also have a circular current carrying conductor which we learn in this chapter. So in this case, if you notice, uh, this is your straight conductor, your normal electrical circuit, and this is cardboard on which the iron filings have been arranged. The circuit passes through the center of this cardboard, which have iron filings arranged. Now, two things are shown. There are two experiments run over here. One, where if you look at the battery over here, positive terminal is here, negative. In this case, it is opposite. Negative terminal is here, positive. So it is just reverse or upside down. Okay. And if we notice, the current flows obviously from positive end to negative end, we know, and electrons flow from negative to positive. Now, if you have a look in this case, the current is flowing from positive to negative end. Okay, that's in this orientation. And notice at how the magnetic field on this cardboard paper is arranged. It is clockwise. Okay, it is clockwise. In this case, you notice it is the orientation of the flow of current is reversed because of the change in the battery endpoints. So here we have negative, here we have positive, which means the current flows from positive to negative this way, and electrons will flow this way, opposite to what we've seen over here. And it is noticed that the field, the magnetic field, okay, on this cardboard paper is rearranged, as in it turns anti-clockwise. That is shown by the arrangement of the iron filings on this cardboard paper. I have a look at both this. And yes, this current carrying conductor is at right angle to the cardboard that is placed over here. Same thing over here as well. And few iron filings have been sprinkled both these places. So when the current flows through the conductor, the iron filing arrange themselves along the magnetic line. And the arrangement exposes the magnetic field in both the cases. So the magnetic field produced over here in both these cases produced by a current carrying straight wire depends inversely on the distance from it and directly on the current passing through it. If the magnetic field is weaker, that means less, that means the distance from the current carrying conductor is greater. So right here outside, the magnetic field will be less because the distance is more. Right over here, where the distance is less, the magnetic field will be greater. That is what it means. On the other hand, it says the strength of the magnetic field depends on the current passing through it. So greater the current, greater will be the magnetic field. That is what it means, the statement. Now the direction of the magnetic field is given by the right hand thumb rule, and we'll see in the next slide what does the right hand thumb rule say. Basically, before we get to that, so that you can figure out what is going on over here and what it means by right hand thumb rule. If you take your right hand, okay, you take your right hand, this would be my right, okay, this would be your right hand, it should be your left hand. So if I show you my right hand, this would be my right hand. Okay. The right on top, that shows you the current, the direction of the current, the thumb. And what you see, the coiled hands or the clenched hand, the fingers, that shows you the direction of the magnetic field. Okay. So if you hold your right hand, okay, and you hold it with clenched this way, okay, further, then the thumb, the direction, the thumb is actually pointing in the showing the direction of the current, and this over here, okay, your curved fingers shows you the direction of the magnetic field. So you can easily make out direction. If you turn it upside down, then the direction of the magnetic field changes because the direction of the current is now downwards in a different direction to the one. So in that way, the magnetic field will be flowing this way. You can try doing it by yourself. Just clench your fist this way and keep the thumb free, and the wherever the thumb points, that is upwards, that will show you the direction in which the current is flowing, and your fingers, which are now curved in, will show you in which direction the magnetic field is being produced. That's the right hand thumb rule which I was trying to show you right now. So you see, your thumb represents the current and also represents the direction in which the current is flowing, that is arrow pointing upwards, and your clenched fist with your fingers curved inside, that shows you in which direction the magnetic field is flowing. Okay? And that's the right hand thumb rule. Now in this case, what has happened is it is just placed upside down. And when you do upside down, the thumb, which was pointing upwards, showing you the flow of current this way, now points downward, showing that the current is now flowing this way. And when that happens, the magnetic field gets reversed. What was first flowing in an anti-clockwise direction now begins to flow in a clockwise direction. Okay, and you can try doing this at home by yourself. You can check it out. The direction in which the magnetic field lines are shaped. That was magnetic field in a straight carrying conductor. Now we come to a magnetic field in a circular carrying conductor. Similar to the straight one, except in this case, the current carrying conductor is circular in shape and not straight. So in this case, you notice that this is your current carrying conductor and the current is flowing in a anti-clockwise direction. Notice how the magnetic fields are produced. There are circular regions over here at both these ends. Have a look. These are your magnetic field lines, by the way. Notice how they are arranged. Okay, circular, 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 and the ones in between, however, they appear to be becoming straighter and straighter as they come towards the center of this current carrying conductor. So what it says is, at every point of current carrying conductor, circular conductor, The magnetic field is in the form of concentric circles as represented here. So concentric circles where one circle is inside another circle, and the other circle is also inside another circle. So what happens is we have concentric circles forming, representing the magnetic field lines. And notice how they are moving, moving in clockwise direction and reverse in this fashion. The circles are concentric in nature with increasing diameters. So you can see that the diameter keeps increasing, which means the circle keeps getting bigger and bigger as it moves away from the current carrying wire. At the center of the loop, I told you the circles appear to become like straight lines, although they are not straight lines, they're just bigger and they're getting bigger and bigger, and it just appears that they are getting straighter. Okay, now just like how we establish a relationship between magnetic field lines and the distance and also the current carrying conductor, here also we look at the similar relationship. If you notice, the magnetic field lines produced by a current carrying conductor, uh, not a straight wire, it's actually circular. This is a mistake over here. Again, similarly, it just like how straight carrying, same applies over here. That it depends inversely on the distance from it, which means that if the distance becomes greater, means the more further it is from the current carrying conductor, the weaker the magnetic field lines are, and it becomes stronger when it is closer to the current carrying conductor. Next thing is the magnetic field lines are directly proportional to the current that is passing through it, which means greater the current, more will be the magnetic field lines. So the right hand thumb rule is applicable here at every point of the conductor carrying current carrying conductor. Now to the magnetic field due to current in a solenoid. We'll see what is a solenoid here. A coil with many circular turns of insulated copper wire, like a cylinder is shown over here, is a solenoid. Okay, so it's in a cylindrical fashion with you can see many coils are there, and these coils consist of insulated copper wires. So one end of a solenoid behaves like a north pole, like over here, and this one will be south pole, because from north poles the magnetic field lines emerging, and south poles you have the magnetic field lines converging. So the magnetic so a solenoid acts just like a bar magnet. It has got a north pole, south pole. From north pole, sorry, the magnetic field lines emerge. From the south pole, the magnetic field line converges. Inside the solenoid, the orientation is from south pole to north pole, just like a bar magnet. Okay. However, the field that is seen inside a solenoid is said to be uniform. Now, the magnetic field inside a solenoid is so strong that it can also be used to magnetize a soft iron. If you put a soft iron inside the solenoid, it will get magnetized. It will become a magnet with the north pole and south. Okay. Magnets that are formed this way are referred to as electromagnets.